Hey everyone, how are we doing? It is time for office hours. If you are here, you get to pick what we do. So go ahead and tell me what you pick as your choice. Just going through here, getting everything ready. Let's take a look. What questions are there? Going through so many things right now. What questions are there? Did this get updated? Got to send an email today. Oh, they're still proving that. Hey, Canvas Content 9. Let's do Canvas Content 9. Good to see you here, Layla. Good to see you here, Leanne. Let's throw out some 100 points also. 2 more days. Oh my gosh. Can we do a man who moves to a new cities? Yes, that's the 2 sample T. So while we're doing Canvas Content 9, good to see you here, Sam. Yo, Sam says. While we're doing that, it'll be the 2 sample T, Layla, and you'll use the degrees of freedom calculator to get the degrees of freedom. You'll use the t-applet to then get the t-statistic. So start attempting that or follow along here with the Canvas content. And then we'll come back and we'll do that here next. And thank you so much, everybody. Everyone's always so kind during office hours and is like, yeah, here, we'll do the next one. So we'll do some Canvas content 9. Let's do this. Canvas content number 9 is due tonight. Oh my gosh. Chapter 15 and Chapter 16. No wonder Canvas Content 8 already due. Let's go ahead and take a look at Canvas Content number 9. Here we go with an example of it. Let's hop in here to the main screen. So this one right here says a new diet is being tested. The inventor, we've done this one. Inventor claims that you can lose 10 pounds. So what is this value right here if it's the claimed amount of weight you will lose? I'm going to go ahead and take this over, but try to solve this notation as we solve this. So we want to know what the notation is. This is so very important to know the notation. We need to know the notation right here. It says calculate the appropriate test statistic. So by identifying the notation, we can hopefully come up with the test statistic. That's going to give us 2 things right here. This is a Chapter 15 question. So what is any of this notation right here? They're claiming you'll lose 10 pounds. Now, the easy one is the sample size. I'll do that one. I'll take out the easy one. So the sample size is the easy one. And we can get something right there from sample size. Remember, this is a 1 sample t-test. This is a 1 sample t-test, which is going to give us the equation. The equation right here for the 1 sample t-test is that the t-statistic is equal to the observed mean, in the sample mean, minus the hypothesized mean over the standard deviation over the square root of n. So that's the equation we use to find out. The degrees of freedom are 24. Great job right there, Sam. Let's go ahead and solve a little bit more. This is the hypothesized mean. This is the observed in a sample mean. And this is the sample standard deviation. It's sample standard deviation, not sigma, because it comes from a sample. We're just going to plug in these numbers here now. So we're going to plug in, we observe a sample mean of 8.5 minus the hypothesized mean of 10. We have a standard deviation here of 6. We divide that by the square root of 25, which is going to be 5. So down here on the bottom, that's 6 divided by 5. 6 divided by 5, that's 1.2. This is going to be negative. Got to be careful. And that's the answer right there, negative 1.25. So we're just solving this out right here, this whole thing. Just be careful while you solve it. I'll disappear here so you can see the final portion of it. When you reduce this down, you get negative 1.5 over, and then the bottom of it reduces down to 1.2. So that's reduced, just solving through this portion right here for this, and solving through this portion for this. You're going to get the t-statistic finally of this right here. So the whole thing solves out just solving through the equation to negative 1.25. Carry all decimals. Make sure to carry them through to the end. And there's the answer. Make sure it's negative. That means we landed below the expected value. A new diet being tested. They wish to show evidence people are not losing 10 pounds. So whenever you see this evidence portion right here, people wish to show evidence of something, that's talking about the alternative. So we're saying the null has the mean is equal to a certain amount, mu is equal to a certain amount, and then we want to show evidence that they're losing less than that. So very careful right there. the claim that they're trying to show evidence of is that less than 10 pounds is being lost. Less than 10 pounds is being lost. A smaller p-value indicates strong evidence against the null hypothesis. This is very true. When the p-value is smaller, we have more evidence against the null. The lower the p-value, the more we can reject the null, especially at lower levels of alpha. Very true. If we construct a 95% confidence interval that does not contain a hypothesized value, which of the following statements is true? So this goes back to what we were covering today when we look at, and we literally just ended on this today. So here, let's go to the lecture screen. This was one of the last things today, and this is chapter 17, and this is a chapter 15 question. We hypothesize that 0 is true. 0 is not contained in this interval. So what can we do to the value of 0? And you see it over here on the test. Since 0 is not contained in this interval, because we're saying I believe the true difference between the scores people make on this test based on using new activities or control activities, I'm 95% confident the difference is between about 1 to 19 points, with new activities having a higher score on average. So I'm 95% confident the true difference is contained in here. 0 is not contained in the interval. 0 is what I hypothesize the difference to be. So what can I do to the value of 0 right here, which you see right there? Since 0 is not contained in the interval, we can definitely do what to the value of 0? And that's our question right here. That is the question we're working on. It says we construct a 95% confidence interval that does not contain the hypothesized value. That's literally what we just saw right there. Which of the following statements is true? We can reject the value. And just take a look at this slide here again. I'll disappear off the screen so you can see it. We construct a 95% confidence interval that does not contain the hypothesized value. We can reject it at the 0.05 level of alpha. If you look, this is below 0.05. On the two-tailed test specifically, this is the does not equals test of the output. So this is chapter 17, but it relates very much to just doing testing. So that's why chapter 15 is very important. And so we can reject it with an alpha value of 0.05. Lower p-values are cause and effect. Someone just help us out right here. Someone solve the last problem right here. Lower p-values show us cause and effect. What do you think? I need someone in the chat just to scream true or false, like true or false. Not as excitedly false there. That is so false. That's as false as it gets. We don't really get, good to see you here, Jacob. We don't really get cause and effect. Tell me I didn't make any errors. Yes, that's what we like to see. No errors right there. No small errors. So easy to make. Oh, look, a little plus or minus on that. That's so nice. That's so nice. A little plus or minus right there in case we do a little rounding, because you still got it if you rounded it. I try to put those on the questions, especially when I go in and correct questions. I like there to be a little leeway on these. Let's go back here and let's go get the My Pearson. I think we're doing My Pearson chapter 17 homework. We're nearing the end. People are going to be nearly done with the assignments. Wait, that's not the homework. Oh my gosh. It's not homework. I saw like 9 questions. I was like, that's too many. Here we go. Okay. We did chapter 16 homework during class. Let's go do the chapter 17. Here we go. Let's head over to the assignment. Okay. Yeah, of course, Jacob. Ask a question. We're free questioner after this. You just ask a question, then we put it in line. We have nothing lined up after this. So your question will be next, Jacob. Your question, we do it next here. You got it. And you just ask your question. You just say, hey, Brian, how do you do this? Can you explain this? And then we do it. That's how office hours work. And so we also give out points. Let's throw out some 50 points. So the biggest thing, I need people to tell me, what's the key to solving these problems? You can tell me in one word or say, Brian, mark your this. What is Brian always going to do when he gets to a problem here? The key to solving these problems is going to be doing what? The key to solving these problems is going to be doing what? You know what? I might do different colors right here. Because these will be the key to solving these problems will be doing what? Always go through and do what to start. Got some color coding right there to help out because we've got different groups of stuff. First thing we want to do is find our this for this. Actually, we can't find the second thing. We're going to, so we'll find it. It's going to be the harder one to find. be much harder. Annotate, mark that notation. Great job, Sam, right there. Let's go get the degrees of freedom for this. This is the sample size right here. Sample size is 20 for each. So actually, you know what you have? You have N1 equals 20, and you have N2 equals 20. Sure, do we have enough room? So N1 equals 20 and N2 equals 20. Both sample sizes are equal to 20. So we travel each route 20 times. That's what sample size 1 means. Sample size 2 means. Feel free to ask any question, Jacob. You don't have to wait till we're done with this one because someone will ask another one, then we'll line it up. So Layla already had this one lined up, and then we just do the next question. So now we need to know what these ones in blue are. If you notice, they're standard deviations. We have standard deviation for route A. So technically, this is standard deviation. Let me see here. I'm going to see if I can answer. It might be a general question. And standard deviation for route B. And we know the sample sizes. You can call this A and B. A and B. There we go. This might be an unlikely situation, but what happens if the alternative is greater than, but the sample comes out as less than? Like, null is that people are 70 inches tall. The alternative is that they're greater than. So then you wouldn't find evidence for that. That's such a great question. What you would actually have in that result, I can draw it out for you pretty quickly right here. If the null is that people are greater than 78 inches tall, well, then the null is where the center of the curve goes. The null value goes at the center. And then you would probably observe something down here. And then your p-value is going to be what? Who can estimate the p? This is like a really quick intersplice question. What's your p-value going to be if you test the greater than alternative? Like if you use the alternative that the true mean height is greater than 78 inches. So now your p-value is going to be what? And what does that mean when you get this p-value? Does that mean you have evidence for that, or you have no evidence for that? So there's I've shaded in the p-value because it's going to look something like this. You're going to be your result. This is your sample result. Your sample mean occurred down here, and then your p-value is going to be shaded like this. So now your p-value is going to be, it'd be very large, which means we do what? You cannot reject the null, and you do not have evidence for that alternative. Now you will have evidence that they're less than. Like if you change this, there is evidence that people are less than that height. So we're not going to accept the null. We either reject or do not reject the null. So we either reject the null or do not reject the null. Now you could reject the null and have evidence that people are less than 78 inches tall, but you can't reject the null and say you have evidence that people are more than 78 inches tall. Does that make sense, Jacob? You would not be able to find evidence for that alternative. You would not reject the null. And you would say, well, we don't have, and that doesn't mean the null is true. You just don't have evidence for the alternative. You're not saying the null is true. You just don't have evidence for the alternative that people are greater than 78 inches tall because you're trying to see if there's evidence for this. Now, you do have evidence that people are less than 78 inches tall, but you don't have evidence that people are more than. That's why we don't accept the null. We're not saying, I believe that people are 78 inches tall. We're just saying we don't have evidence for the alternative. We don't have any reason to show that the people are greater than 70 inches tall. That's why we don't accept the null as true. So that's another good reason to say I don't accept the null as true. It's just that we don't have evidence for this Stats is a weird thing. We talk in a weird way. People are like, why do you talk this way, stats person? And I say, I don't know. Stats changed my brain around. It's a very scientific, like exact way. Like, I'm not saying this is true. I just don't have reason to doubt it. So I don't have reason for the alternative. I don't have reason to believe the alternative you're offering to me and reject my null hypothesis. Because you're saying to me that people are more than 78 inches tall, and I'm like, nah, that I don't got reason to believe that. Now, you could convince me people are less than 78 inches tall, but you can't convince me people are more than 70 inches tall. I'd reject my null for the other one, but I wouldn't reject the null for the first one. So, Jacob, such a great question, Jacob. Like, kind of just understanding, like, well, why would we reject? Why are we going to accept? No, we don't accept. We just don't reject the null. And so we've got all the notation marked here for this question. Everything's marked. The mean for group A, the standard deviation for group A. Nice job, Layla. Great job. I'm guessing you went to the T with the degrees of freedom calculator. Excellent work. Great job. That's what I like seeing. So we're going to pull up the 2 sample T degrees of freedom calculator. He travels each route 20 times, standard deviation of 5, standard deviation of 3. This gives us the degrees of freedom right here. And now we need to go to the T applet. So now we're going to go over to the T applet right here and put another question in the chat, Layla, if you want. I'm assuming people who are going to watch this later probably want to see how we solved it. But great work. It really goes down to marking that notation. Great job, Layla. We're going to draw out some more points. Why not? Let's just go crazy here. Why not? 200 points. People are going to get some crazy points. We're going to put in our degrees of freedom, which give us the shape of the t distribution. What kind of confidence interval are we building? Where'd the question go? We are building a 95% confidence, so we need to go here to the between, and it was actually showing us a second ago. But we're going to get 2.04. Oh, definitely. Let's do that one's going to use jump. So if you're working ahead, you don't need to, but if you're working ahead, that one uses jump. So the t with 31-ish degrees of freedom for a 95% confidence interval was 2.04. Now we have all of our notation, and we need to do y bar b minus y bar a. That's one of the common mistakes on this problem, because they do b minus a is equal to plus or minus t star, technically, and then the standard error, which is s sub 1 squared over n sub 2, n sub 1, oh my gosh, plus s sub 2 squared over n sub 2. There we go. Let's start plugging in our numbers, and it just becomes an algebra problem now. So route B took 46 minutes. This is a difference of 2 minutes. Plus or minus the t of 2.04, square root, standard deviation 5 over 20 squared plus 3 squared over 20. That's 34 over 20 square root. Just adding those together. 34 divided by 20 square root times by 2.04. And there we go right there. That's the margin of error. And it's 2 plus or minus that. So I'll show you. I'm afraid someone might be wondering how I got this. So the inside of this solves to 2 plus or minus. Can you show the t calculator? And yeah, CAD. Thanks for asking, CAD. That's 2.66 plus or minus 2.66. That's just what all that solves to right there. Are you talking about the t? So the steps we go to are, first you have to find out your degrees of freedom. The degrees of freedom give you the shape of the t distribution. This was obtained from sample size. He travels each route 20 times. Standard deviation of route B or A. Since it's 20 and 20, it doesn't matter which one I put, because you'll be able to, wait a minute, wasn't B a standard deviation of 5? It'll still give the same degrees of freedom. So this is how we get the degrees of freedom. Once we get the degrees of freedom, we have to go over to the calculator, and both of these are in the chat right now. You can see the t-applet, Mubal put it in the chat. You can see the t degrees of freedom is in the chat also. And you can see right here, I might not have shown that, but the 2.04, I might have been blocking it by accident. This right here is for a 95% confidence interval with the degrees of freedom that we just calculated over here. The degrees of freedom, once again, show you the shape of the t distribution. Where it has less degrees of freedom, it's more flattened out, and the t is going to be wider. So we had 31.11 degrees of freedom. That's where the t is coming from that I'm using right here, is based on the degrees of freedom, which we have to calculate using one of the applets right there. And now we get it, 2 plus or minus 2.66. Let's go ahead and try that. So 2 minus 2.66, there it is, negative, and then 4.66 should be right. Excellent work. Yeah, good job right there, CAD. Great work. Excellent work. Should man believe 5 minutes? Oh, we got this one wrong during class. No, he should not believe it because it's outside the interval. The interval does not contain it. Now I know how to look at intervals and see whether or not it contains it. Let's hear. We'll put a break and then we'll do this question right here. Take a little sip of coffee. Come on, straws. What you doing? All right, let's do this question right here on the adults and children's cereal. I miss sugary cereal. What is the formula again? So to CAD's question real quick, the formula we're using is right here, CAD. So no worries, CAD. Great questions. The formula we're using is right here. And take a look at all the notation right there for this one you're solving. So I've got all the notation marked up there. I'll go away. I've got all the notation marked up top for that previous problem. I might put another break in the video right here. But does this make sense right here, CAD? That this is the formula, y bar, the mean of route B minus the mean of route A. So you can see the mean of route A, mean of route B. And it's just that they solve it B minus A. I think the problem, let's just take another quick look at that. They mention right here. This is where they're showing you they're doing B minus A. So that part right there I might have not mentioned clearly enough. You might say, well, why are you doing b minus a? It's just the way they solved it. They solved b minus a right here. So when you solve yours, you have to go in and also solve it doing b minus a, doing the sample mean for b minus the sample mean for a, plus or minus the t statistic found from the t calculator. So you have to use the degrees of freedom calculator. And then the standard deviation of route 1, the sample size for route 1, which both of them have the same amount of times traveled. And then the standard deviation for route 2, which is over here, which is route B technically. These could be A's and B's, like A, B, B. Does that make sense right there, Cad? And Cad, thank you so much for asking those questions. We're going to do the next question here. I'm going to throw some more 50 points. The office hours are here to help. So if you're here, you definitely get to ask the questions and say, hey, wait a minute, can you explain this a little bit more? You're welcome, Cad. Great work. My contact is going crazy. Let's hop back here to space real quick. Okay, so don't worry about, I really want everyone, if you're here and you're working on the question, you get to ask like, hey, can you explain that again? Can you show me that formula? Where did you get this from? Please ask that. That's what we're here for. Of course, people use the videos later, but when you're here live, you get to ask all the questions. Let's do this. Next question, here we go. Okay, here's the next question right here. We've got the adults versus children serial. This is a question we're going to use jump for. So it's going to give us some good practice of reading jump output. So we're going to go here to copy to clipboard, clicking the little mark right there. And we're going to hit Control-C or Command-C. Control-C or Command-C, Control-C on a computer, on a PC, Command-C on a Mac. And once you do that, you're going to copy this. Please notice it has column names. Column names are when you see the first column has a name in it. That's a column name, just like a title of the column. You're going to go over here to anywhere in jump. You can be anywhere in jump. On a Mac, you'll see it up at the top. On a PC, you'll see it right here. You want to go to File, New, Data Table. You can be anywhere in jump. File, New Data Table. Once you're in the new data table, do not click inside of it. Do not click inside of it. You already clicked inside of it, didn't you? Well, then go to File, New Data Table again. Before clicking inside of it, go to Edit, Paste with column names. And that's key right here. You have to paste with the column names. So when you paste with column names, these will be blue. They should not be red. If you did not paste with column names, or sometimes people click inside of it, and you see now it's not even letting me paste. That worked. You might be able to click inside of it. I've just seen more errors. This is correct right here on the right. This one on the left is wrong because it treated it like categorical data, and that's what happens when you don't paste with column names. Just restart and paste with column names. So once you have everything here, make sure to be very careful and paste with column names. We're one step away from having the data ready to analyze. I'll slow this down. Go to Tables. Go to Stack. Tables Stack is going to stack the two columns on top of each other. So Tables Stack. Once you're in Tables Stack, double-click Children Serial. Double-click Adult Serial. With both of them double-clicked, they go over to the stacked columns. Make sure everything looks like this. And then go ahead and click OK. Now with both tables stacked, we get a new data table. Notice how we have the label. You don't have to expand these, but take a look. Like which serial label do we have? Do we have a children's serial or do we have an adult serial? And then the data is how much sugar content was in them. So let's go ahead and analyze this data now by going to Analyze, Fit Y by X. With the Analyze Fit Y by X, we'll be able to look at comparing the two means of the groups to each other. So now we're going to ask, does the data, which is the quantitative variable, how much sugar is in there, quantitative Y, is it explained by the label, explained, which is a categorical X variable, putting it into two groups? So we're just asking, is the quantitative Y explained by the label? And let's go ahead and click OK. So now you can see there's a big difference right here that the children's cereal has way more sugar in it and the adult cereal has way less sugar. Once we get this sort of analysis right here, and make sure you have this analysis, we're going to go right here to the following. We're going to go to the red arrow, and we're going to go here to t-test. And the t-test is going to do a 2-sample t-test, and let's do it. Zoom back out, and here's the results. And that's it. What is 36 divided by 2? Well, 36 divided by 2 is 18. There's some decimals we're not carrying. This, once again, just to point out, the t ratio, which is not the t for the confidence interval. Talked about that a lot during class today. The t ratio right there is going to be, U-Bot's talking to us all, just the difference standardized. And they're carrying a few more decimals than I am in the background. But the difference divided by the standard error is the t ratio right here. The degrees of freedom, which we don't need to calculate, but is done for us, is the shape of the t distribution. We obviously reject the null of 0 on the two-tailed test because the difference in the amount of sugar content is somewhere. I'm rounding this. I'm 95% confident the difference between adults, children's sugar content, and children's sugar content in cereal is somewhere between an average of 32 to 41 grams of sugar on average. On average, children's cereal has that much more sugar, and that's why it's awesome. Get some Lucky Charms, some Honey Smack, some Fruit Loops, all the good cereals. Don't eat some like Fiber One, horrible cereal. So here's the lower bound and here's the upper bound telling us that we think the true difference between these means is somewhere between here. We observed a difference of 36.32. That is our observed difference right here. The degrees of freedom, once again, is the shape. The t is the standardized difference divided by standard error, and the lower and the upper bound. The confidence interval has a margin of error about 4.5. You can get the margin of error of the confidence interval by doing upper minus lower. This is how far those numbers are apart, divided by 2, and I said it's about 4.5. It's about 4.5, and that's just half the length of the interval. Good thing we should know, half the length of the interval is the margin of error. So let's take our output and put it in and get the answer. Okay. So we just want the confidence interval, 2 decimals, 3188. And then I think it's this. Good. I am 95% confident the true difference between adults and children's cereals and sugar content is that children's cereals average between this and this much more content than the adult cereals. And so that's what we're saying. Pretty good interpretation by them right here. That the true difference is that children's cereals have about this much more to this much more sugar content. And that's because it should be pretty clear to see from the output. But the difference here is also positive because we're doing it children minus adult. And that means we're subtracting the mean of children from the mean of adult. We can also take a look at those means. If we go here to the mean, oh, we can do a means instead. Look at that. Yeah, you can see the mean for adults was about 10.5, and the mean for children was 46.8. That's a difference in means of 36.32. And they do individual t-tests on this right here. This is individual t-test to figure out for an individual mean. So you can get 95 or individual t confidence intervals, t intervals right here. Good stuff right there. We are open on questions. We could do the rest of this homework right now. I guess we're almost done with this homework. I think this will be a great one to do right here. We'll put a break in the video. But this will get us pretty far with the homework. Let's put a little music on. Okay, let's take a look at the hot dog question. Let's take a look. A study examining the fat content in grams for samples of beef and meat hot dogs. What is a meat hot dog? Beef, meat. What is in that hot dog? The resulting 93% confidence interval for the true mean of meat minus the true mean of beef is this. When we look at this interval, in a recent poll, 1,000 selected adults, present approval rating, you bet. Let's do that one next, Cad. You got it. Complete parts A through C. So when you look at this interval, it contains 0. It's a pretty important thing. We're saying that the difference between the beef and the meat hot dogs might be 0. So since they have opposite signs, that's what that's telling. It's that the beef hot dog might have more fat because of the negative, or the meat hot dog might have more fat because of the positive. So somewhere between, on average, meat hot dogs have 1.7 more grams of fat on average, or it could be up to beef hot dogs have on average 2.6 more grams of fat. So which one has more fat? I don't know. I don't know. We're unsure. Awesome. Got a grade. We got Cad's and Leo's question next. So there we go. There we go. Awesome. What does the fact that 0 is in the confidence interval mean? Well, 0 might be the difference. It might be that there's no difference. So the difference is insignificant. That's what it means for it to be insignificant, that there is no significant difference. We don't have evidence of a difference. There is no difference between the two samples. No, there was a difference. The difference between the two samples, because that's the only one that almost caught me off guard there for a moment. If we want to find the difference between the two samples, we need to average together the two numbers. So to average together the two numbers, we're going to take and do 2.6, and we're actually adding these numbers. And the average of these two numbers is 0.45, actually negative. So that's the center of the interval. The center of the interval is down here at negative 0.45, because it's actually upper plus lower divided by 2. So that's the lower. So if we technically do it, it'd be Upper plus lower divided by 2. I'm just like making sure it's negative. It would be negative because it's more down there. Lower divided by 2. Yeah, so would that should still work. Let me do it that way, the proper way. Upper plus lower divide by 2. Same answer. Awesome. We got some good questions right here. So the difference in the two samples is insignificant. There is a difference between the two samples, but it's insignificant because zeros contain the interval. What is the corresponding alpha level? Well, when we do this test right here with a 95% confidence interval, then the alpha level is just 1 minus that. So corresponding alpha level is 1 minus the confidence interval, 93% confident, and 7% alpha. Let's go over here and do the next question. Let's do it. Kad's question is, in a recent poll of 1,000 selected adults, presidential approval rating, we just played that one, was 46%. Okay, chapter 16 quiz. Let's go find that one. Chapter 16 quiz. Where'd it go? I'll find it, and we will do it. Chapter 16 quiz. Okay, in a recent poll, I'm finding it right now. Hey, we found it. Here we go. Okay. In a in a recent poll, 1,000 randomly selected adults, presidential approval rating was 45%, making 90% confidence interval for his approval rating by adults in the country. I love this question. This is such a good one. Let's go and grab it right here. Bring it over to Word and solve it. Okay, I need people to help me with the notation. Cad, help out here with the notation. Layla, let's do this. Let's get some notation knocked out. Oh my gosh, we're going to throw the pen. First time today. So there's a notation, there's a notation, there's a notation. We're going to get two things out of this. And I'm going to put some David M. Lane in here, because we're going to give a number. People are going to wonder how we know that number. Great job, Cad. Excellent work. And over here, we're going to... I want to see if you can get that one. I'm going to go to the David M. Lane while Mewbot brings up the David M. Lane. See if you can get what that 45 is. That's usually where people get stuck. I'm going to show you... So this will give a hint of what we're doing. So here's the 90%. When we go to between, make sure you're doing between. It's 1.645. And let's see what we have. So this is where people usually get stuck, especially with the 45. We're asking, do you closely? We should be back now. Sorry, this happened twice today, and I hate that. It shows me the stream disconnected. We should be back. So sorry about that. I saw that blip in the radar. This one is going to be P hat, because why is this P hat here, Layla? Good question right here. Why is that P hat? So why is that one right there P hat? Why is that one right there P hat? And think about how it's connected to this right here. So why is this now P hat? So then you'd be like, oh, okay, that's P hat because of this. P naught is going to be the hypothesized if we're saying, let's see if this is true. Which actually, you know what's funny? Actually, Layla, you are correct. In this example, they're going to use, they're going to actually, it might be that I got a version that used the same numbers. Now they're calling it P naught right here. So they are calling it P naught down there because they're just using it in a different way, just by saying, hey, let's test this. So if you notice right here, this one is being tested by the null hypothesis. But then over here, this one up top is from a sample of 1,000. We observe 45. Does that make sense? From a sample of 1,000 people, 45% of them said they approve of the president. That makes this P hat right here because 45% of a sample. We're down here, we're saying, well, then let's test 45, which is kind of weird. I might have just gotten a version of the question that uses the same number twice, but now they're testing it. So they just happen to be testing, which we are definitely not going to reject that value here. But does that make sense, Layla, that they're testing it and the z-score we found just a moment ago for the 90% confidence interval is a z-score of 1.645. And so now we get p hat plus or minus a z-score square root p hat q hat over n. So all this right here. Can everyone still hear and see me? I think we're still streaming. No one said anything since we had the disconnect reconnect issue. There was one time where I talked for like 30 minutes and I wasn't even streaming. Let's hope that's not now. Nice, I think. And yep, Cad, you are correct. 1.96 for a 95% confidence. If you ever need, so here's the other ones on the screen right there. There's 98. There we go. Great job. And 80% is 1.282 or 1.2816. So try to remember. I don't know. I just like memorizing stuff. So let's go ahead and put awesome. No worries, no worries. I was just worried that since the stream, I don't get it. It's done it twice today. It did it during class. And then I've heard someone was talking about internet providers since COVID. And they were like, because of the increase to internet usage, internet providers like with Netflix and everything have been like throttling internet and messing with internet and causing more like inconsistent service. And you know what's interesting? I've noticed it. Before, when I streamed from my apartment in Knoxville, I didn't even have gig speed internet and I had worse equipment and I had better stable internet. But we've had more, we'll be watching Netflix and it'll be like a connection issue has occurred. I just didn't have those things before. I mean, I don't know, it'd be interesting to poll people and be like, has your internet gotten worse since COVID? And it could be because of the increased usage, but, or it could just be we are using the internet more and so we see more issues. Either which way, I swear I'm seeing more issues. There's the margin of error, which is not good when you stream a class. Maybe this weekend I'll buy Starlink internet. I should just do it. Say to heck with it. Get some Starlink internet. Some Elon Musk internet here to save us all. There we go. We've solved it. And let's go ahead and solve. Does it want? It wants it as decimals. I don't know if anyone else feels that way, but I do. 0.476. And then, so 0.424. And we do not reject it. We fail to reject it because it's exactly in our interval. Yes. I think they don't always do the exact, really? Really? Are they always testing the exact same value? That's ridiculous. So you'll never reject it because they're always testing the same value. It actually is changing the question now. Yeah. Which one? You want to do the chapter 16? Which one did you want? Which one did you want? Customers spend more on trip A or trip store B or store A. Let's do that one. Lay last that one, and that's a chapter 17. So yeah, go ahead, Sam. Ask any sort of question you want. So Sam, go ahead, pull one in the queue right here. What chapter 16 question? Layla has a chapter 17 difference between two means. And notice how I know when she says store A versus store B, I'm like, okay, that's a difference between two means because we're going to compare the mean of store A and the mean of store B. So I can identify, knowing what the chapters cover, is that we're comparing two groups right here, which is comparing groups for chapter 17. So do customers spend more at store A or store B? And let's take a look at that. And then we can do any other question. You got it, Sam. You got the next question up here. Here we go. Do customers spend more at store A or store B? Let's do this. Okay, we got do customers spend more at store A or store B? And we've got a table of the output right here. So the null always has the equal sign. Yes. Yes. That eliminates one answer. What does it say? Suppose the researchers decide to test if the means are equal. Awesome. Great job. Which one of these would be the answer? A, B, C, or D? The researchers want to see if the means are equal. So that's all we know right now. Yep, it's going to be B. Yep, because they're seeing if they're equal, so the alternative would be if they're not equal. They didn't give a direction to the test. So you always like look to what the researchers are testing. They want to see if they're equal. We're going to see if they're not equal. Like we're seeing, are they equal? Or are they not equal? It doesn't say less than, greater than, so we're not going to do that. Remember, the null has the equal sign. That eliminates this one as a possible choice because the null has the equal sign. Compute the test statistic. Okay, so let's go compute the test statistic. We need to go take this output right here. And I think they're doing A minus B. Okay, good. Since they're doing A minus B, let's go grab the output. Put it in the center nice and neat there. The test statistic is going to be calculated from y bar A minus y bar B. And plus or minus, what am I doing? That's a confidence interval. Standard error, S sub 1 squared over N sub 2, or we'll use the A and the B because they've got A and B. S sub A squared over N sub A plus S sub B squared B over N sub B equals to a T with whatever degrees of freedom we will find here shortly. Plug in the numbers. Let's do it. Numbers, time to go into the equation. Okay, so there we go. Just going to plug in the numbers right here. Yes, Layla, that looks to be right there. The means are 44, 54. That's going to be negative 10 up top, divided by the square root of all this. 20, 19. This feels like it's that year still. 84, and then 82. Be very careful with your squaring of stuff. This is where errors are going to occur with the mathematics. So 20 squared divided by 84 equals that. 19 squared divided by 82 is this, plus the two together. I think I hit it correctly. Okay, I think I've done it. And then we're going to square root this, 3.03. Oh, yeah, it rounds to that. Hey, 3.03. And then we're going to divide the difference up top of 44 minus 54 is 10. Divide that, and we get a t-statistic of negative 3.303. So with this right here, we're just going to take, we're not going to misclick. Don't do that. We're going to plug in this test statistic. Not doing that. We're going to plug in this test statistic right here, delete it down to 2 decimals, and there we go. Now, what's interesting is I can tell you the p-value. The p-value for this is going to be this. I'm going to bet some money on that. Yeah, it's going to be that. We reject the null. There is evidence that they're not equal. How'd I do that? How did I do that? How did I get that p-value right there and I know it? How did I know that? Let's find out. So we need to first find the degrees of freedom. So the degrees of freedom for this, we have to do a little bit of work. Remember, we have this right here with the sample size, 84, 82, 2019. So we're just going to keep that in our head for a moment. Let's go ahead and bring the degrees of freedom calculator over to here. And we have 84, 82, 20, 19. The degrees of freedom are 164. I'm going to round that to 164. So now that we have the degrees of freedom, let's go over to the t-applet and put this in here. And we're doing the two-tailed test. So with the degrees of freedom in, we have the shape of the t. And now we put in the t-statistic we found of 3.033, or it was 3033, and look at the p-value. So what did I do and how did I know this? So, well, so Layla, think about this though. Do you remember the normal curve when we go to a z-score of 3 and you go to the area outside of it? Well, if you go a little further over, because we have 303, the normal curve is just like the t. And so I knew this was the answer for the normal curve, and I went a little bit further over because the t is basically the normal. And so you still have about the same answer. It's the same answer on the normal. And then I was like, okay, we're a little bit further over, so it'll be a little bit smaller. It's probably about 0.001 at this point. I was like between 0.001 and 0.002, and that's how I'm getting this answer right here, is I had to find the degrees of freedom. And so this is basically normal at this point. So I just used my knowledge from the normal to solve the answer. I knew that was 0.003 because of the 99.7. And then I just said, well, it's going to be a little bit smaller than that because we're further over. Is that making more sense, Layla? If mine is, yeah, yours will be 0.0001 also. You'll enter in, so technically we need to do the negative. That is correct. But yours will be even smaller. Yours probably is just, it's saying like basically 0. Your degrees of freedom should be pretty similar. It's going to be basically 0. Is this making sense how I'm doing this right here, Layla? And would it have given to me if I did that? It does say that's correct. Would it have given to me if I did this? Nope. So I was between this answer right here, and I was between this one. And it might even give it to me if I say 0. Because I'm guessing yours is 0. And it would give it to you right there. It would say that's correct. So it's got 0.001 plus or minus. Will it get mad if we do this? Oh, really? Really? Because if you don't round it, it won't give it to you. But if you enter in another decimal, it will give it to you. So you don't want to go over here to R and put in the following because it would get mad. Oh, I did capital P. What? Capital X. And I think Sam has a question. There's the exact p-value calculated more exactly. We could take that. There, oops. Whoa. There we go. There's the exact p-value calculated to more decimal places. Yeah, it is confusing, and we have more exact ways of calculating it. We can carry out more digits. Like, this is why, using applets like this and stuff, you can carry out more digits, and like the applets are limited in what they can do because they only display so much on the screen. So you don't really get a really, really fine answer on what this is. But if you're over here on something like R, you can go ahead and let me change this back to 7 digits again. So there we go right there. So you can get a more refined answer, which you don't need to do that. We're just showing right here that you can't get the, like, when I put in my degrees of freedom of 164 or something, and I put in my t-value of negative 3.303, it's telling me this p-value here. But over here in R, I can get a really ridiculously exact answer. Like I can be like, oh, here's the p-value. But then the applet, instead of saying 0.000117, yada, 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 the applet's going to say right here 0.0001. So you don't need to know all that extra stuff, but I do find that kind of cool. I think Sam has a question. Let's go do Sam's. Before lending money, this is chapter 16 right here. Yes, it's 16, right? Yep, 16, correct. Let's do this. Put on music. Good practice here, everybody. Getting all the practice, getting all the questions done. Chapter 16, quiz question. I just like that we can get exact answers. Like the applets get you so far. And then if you really want, you can go and like, be like, oh, let's find out the exact answer. Let's go like super crazy here. Before lending money. Chapter 16. Here we go. Let's hop back here. Okay, we got before lending money. A bank must decide whether they believe an applicant will repay the loan. One strategy used is a point system. Loan officers assess information about the applicant, totaling points they award for the person's income level, credit history, blah, 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 blah. The higher the point total, the more convinced the bank is. It's like evidence that it's safe to make the loan. An applicant with a lower point total has then a certain cutoff is denied a loan. So you need to have a high enough point total. We can think of the decision as a hypothesis test since the bank makes its profit from the interest collected on loans. Their null hypothesis, this is about all that matters, is that the applicant will repay the loan. That's the null. If the person's score falls below the minimum cutoff, the bank will reject the null hypothesis and deny the loan. So what is the null hypothesis? The null hypothesis right here is that they get a loan. We're going to give them a loan until we have evidence Okay, Sam, you got to help out here. You got this? We're going to look at that null and say it's what in a type 1 error. So we should do what? In a type 1 error, we're going to look at the null and we're going to look at it and say it's what. In a type 1 error, it is what that we should do what. We're going to look at that null for the type 1 and we're going to look at it and we're going to say that is this. Type 1, look at it and say that is this. So we look at the null, and for a type 1, we say the null is, and there's what we're going to say about it. Type 1 error. Type 1, the null is this. Or 1, we're going to say it's true, but we reject it. So it's true that they'll pay back the loan, but we're going to reject that and not give them the loan. So it's true that they would pay back. What kind of error is made when the bank misses an opportunity? That's a type 1. Because in a type 1, it is true that they'll pay back the loan, but we don't give them the loan. So the bank misses an opportunity. So it is true that we should give them the loan. Does that make sense? In a type 1, the null is true. We should give them the loan, but we reject it and say no loan for you. Does that make sense, Sam? In a type 1, the null is true. They would repay back the loan, but we reject that and say no loan for you. So we miss an opportunity to give them a loan. Well, then the type 2 is going to be the reverse of that. In a type 2, the null is false, as in we should not give them the loan, but we fail to reject that. In a type 2, the null is false, and we fail to reject it. So when a person defaults on a loan, as in we give someone a loan that they should not have gotten, that's a type 2 error right here. Suppose the bank decides to lower the cutoff score. So what are they doing right here? Would this be analogous to a higher or lower level of alpha? So they're making it so more people get loans. So my brain halfway breaks on this. Yeah, we can do the next CAD. You got it. So if they're making it so more people get loans, what are they doing? I want to see what people say. I'm thinking about it too for a moment. They're making it easier to get loans. Now that I think that's going to make you say the opposite of what we should have right here. If they're making it easier to get loans, then they're making it, yeah. If they're making it easier to get loans, then they're making it what to reject the null. They're making it easier to get loans, so they're making it whatter to reject the null. They're making it easier to get loans, so now it's whatter to reject the null. It's easier to get loans. So now they've made it easier to get loans, so the null is whatter to reject. And we can think about how that relates to alpha. If they made it easier to get loans, then they're making it whatter to reject the null. The null, we reject it when the p-value is below alpha. Harder, so alpha is going to go up or down. So alpha would be lower or higher because it's harder to reject the null. It's easier to get loans. So we're saying it's way easier to get loans now. So it's going to be, it'll be a lower alpha because it's harder to reject the null. Does that make sense? This one's so tricky because they're making it easier to get loans, which means it's harder to reject the null. So it's going to be a lower alpha. Because remember, when do we reject the null? When the p-value is below alpha. Does that make sense? This one is super tricky. It's definitely caught. Watch me get it wrong. And they'd be like, "I told you, Brian." But alpha is when we reject the null. So if we were to lower alpha, we're making it harder to reject the null, and more people will get loans. Yeah, no, don't worry. It's so tricky right here. Let's throw out some 50 points. So we're going to have a lower alpha. So they're making it harder to reject the null. What impact does this change in the cutoff value on the chance of an error? What impact does this change in the cutoff value? Okay, yeah. So it's going to what? So they're lowering alpha. So they're going to have what right here? If they're lowering alpha, they're going to have what? I'm just like double checking my brain. Like if I reverse the previous question, which one do you think? If they're lowering alpha, like I know theoretically, I'm just like making sure. Yeah. So if they're lowering alpha, what is this going to have? And so we can go back to our notes from today. And the notes make it very clear. We're going to increase the type 2. Exactly. If you lower alpha, we can go reverse this. Can we reverse this one? If you lower alpha, you'll increase type 2. So we did lower the alpha. And alpha is type 1 error. So we're lowering our type 1. So just theoretically, we are decreasing the type 1 by decreasing alpha. And we are increasing the type 2. So decrease, increase right there. It has to be. There we go. It just theoretically has to be. The one to make the mistake on is this one. If you're lowering alpha, you are decreasing type 1 error because that's literally what it is. We've got it right here in the notes. that type 1 error is your alpha. So if you lower your alpha, you're lowering your type 1 error, but inversely related to that is your type 2 error, which is your beta. This one didn't really mention beta, but beta is the type 2 error, but your alpha is inversely related to beta. So by alpha going down, you decrease your type 1 error, because that literally is what it is. Like alpha is literally type 1 error. And then that would increase your type 2 error, which we know is beta right here. And then 1 minus beta is power. So your test would be less powerful, which you'd have the less ability to find people who should not get the loans. So that's what it would mean. In context right there, good stuff. Layla has the next one. Researchers are investigating drinking glass size. Let's do it. I'm going to go find that question. Let's do this right here. And let's go find the drinking glass size question. And here we go. Next question. If you have another question, let me know. We're going to do the drinking glass size of water. And great job, everybody. Working ahead. Only a few more quizzes. You'll be done. Oh my gosh. Drinking glass size question. Yep. Just saw it. Here we go. Let's do the drinking glass size question. Here we go. Researchers invest how the size of a drinking glass affects how much soda people tend to pour themselves. People are randomly given either a 17-ounce or a 25-ounce glass. Don't know those glass sizes. And they're invited to pour. Would you like to pour soda in it? The glass size, did the glass size change the selected proportion? The summaries are shown to the right. Assume any assumptions and conditions are satisfied. Condition 1, random. Condition 2, 10%. Condition 3, nearly normal. Condition 4, independent means. So what would we have for the null hypothesis? And this is pretty good right here for your project, because it's kind of showing you how to do the things in the words. So kind of makes clear right here that the alternative, you could write this out basically, but the null always has the equal sign. So if it's equals, then we're going to say they are the same. Now the alternative, they don't give a preference. So since there's no preference given to the people pouring more in the large glass or the small glass, we're going to have that it's not equal because no preference was given. So is there a difference between the two? Is there a difference between the means that is non-zero? Find the t-test, find the p-value. Well, we're going to have to do some statistics here. Let's go ahead and take the table, bring it over here to a Word document, and start solving through the mathematics right here. After Layla's you bet. Oh yeah, we had that one next. Yeah, you got it. You got it, Cad. Sorry about that. Forgot about one for a second there. Thank you so much for reminding me. Let me throw some 50 points. Yep, we can do that one next after Cad's. Yeah, no, Layla's right. Sorry, I forgot about Cad's. I'm sorry. I know people aren't mad. Everyone is so chill. We're doing the t-test. Okay. I didn't know if we're doing a t-test or conference roll. The t-test is y bar. Which way are they doing it? I gotta see if they're doing 1 minus 2 where small glass. Okay, they're doing small glass minus large glass. Very important right here. We see that this is small minus large. The mean of the small minus the mean of the large. And then down here on the bottom, we have the standard deviation. The standard deviation. Oh my gosh. That is correct, actually. Standard deviation for the small glass over the sample size for the small glass plus the standard deviation for the large glass squared over the sample size for the large glass. Exactly. It's all just help for the future. So this is going to solve out to the t with the degrees of freedom. Let's go here and actually just plug in the numbers now. The decimals, why you got to be decimals? I guess decimals exist, so we should learn how to deal with them, right? We don't like decimals. No decimals here. So we're going to go ahead and plug in the standard deviation of 1.73, square that. Take this over the sample size of 24, add that to 3.01 over 29. Got to square that. Don't forget to square it. This is all going to equal up to the t with the degrees of freedom. We'll find those degrees of freedom in a second here, which shows the shape of the distribution. But we need to take 1.73 Square that divided by 24. Copy that. 3.01, square that, divide by 29. Add the two together. There you go. Square root. And that is the standard error. Everything we just did right there, make sure to carry your math carefully, is the standard error. So now we just need to take the difference. Large glass. Oh, wait. Ooh, I got a problem right here. I can't move these, can I? I reversed the numbers. I reversed the numbers. Someone's saying, oh no. It's small minus large. Watch out. I was like, that's interesting. People poured more in the small glass. So watch out. Don't do what I did right there. We need to do small minus large. And there's the small mean, and there's the large mean for the sample that we took. So there's the standard error. Now we do 5.42 minus 6.76. And we divide by the standard error. Ooh, we got something nice right here. 2.0267. 2.0267. And I love it whenever these are close to whole numbers. And we're going to put in the t statistic right here. Does anyone have a guess of what the p-value might be? And I just want you to think like it's like a, I just want you to think like it's a z-score for a second. I want someone, I'll throw 100 points if you can get this. Oh, what alpha level are we using? Oh gosh, this is tough now. Oh, this is so tough. Oh, it's gonna be so close. I'll show you. To get the degree, to get the p-value, it's a little bit of work right here. We need to go over here to the degrees of freedom calculator. It's going to be so close. It's going to be like 0.052. It's going to be, I think, just a little bit above 0.05. So we need to go to the degrees of freedom calculator, which is on the screen. And once we go to the degrees of freedom calculator, we're going to enter in the values. The values we need to enter in are the mean for group 1 and the standard deviation for group 1. So there's mean for group 1, mean for group 2, standard deviation for group 1, 1.73. And the degrees of freedom are basically 46. I'm going to round that up to 46. This one doesn't take decimals, so sometimes it's better to round it. And then we're going to take our t statistic right here and do the two-tailed test. I said 0.052, and the answer is 0.049. Wow, that's close. Wow, that's close. And wow, that would change dramatically our answer. So once again, we got the degrees of freedom from the calculator. Here's the t. I half want to go and look at it inside of R really briefly. It's a two-tailed test with a t statistic of the following. And the degrees of freedom were found to be, got our degrees of freedom over here. Oh, we got so many of these open. Where's our degrees of freedom? I want to see the exact. I want to know very exactly what this p-value is because I don't want this problem. Yeah, it's 0.049. So there's the exact. Your answer would be just fine right here. Going over here, you can see we have the degrees of freedom calculated, which tell us the shape of the t, and there's the p-value right there on the two-tailed test because we're doing a does not equals test. Very important to know that this is a does not equals test because right here, and that's a two-tailed test, the does not equals test. 3 decimal places on that, 0.049. So we reject the null. The data provides sufficient evidence that there is a difference right here. I really haven't read up too much. What does BS focus on? Yeah, that we have done in this class. Great question right there. And with sugar, all right? Oh my gosh, are you crazy? What is going on right here? Is it mad about this p-value? It better not be mad about the p-value. It is mad about the p-value. Round to 4 decimals? Really? Oh no. Oh, just please tell me if you get this wrong. It wanted 4 decimals. It's wanting you to be crazy exact. If you get that wrong, please tell me. Once again, everyone knows you can email me about this. That's a bit of a problem. Please tell me if that one counts wrong for you. Not happy about that right there, that it told me that was wrong because I didn't include that extra 8. Because our applet does not show that. There is an applet that can let you do this. It's ridiculous. I'm going to put 5 points on this exam in case anyone's not watching this. Just because of that, let's throw 5 points on this exam. Please email me if that one's wrong for you. I did enter in this value right here. There is a way to get this with another applet. So let me go grab that extra applet. And then I can answer, okay, here's the T applet. Here is, and let me put it in here. And let me go grab the T statistic. And let me do the does not equal. So let's bring this over. Oh, that's the wrong one. There. Really? Oh, because I didn't round it. Man, this one, yeah. It's a good problem. It just, that last part, and let's copy this. 0.0485. Would it give it to us? That's correct. Oh, wow. It's too fine of an answer. Very interesting. Accepts very interesting range of numbers. There it is. So it's all the way from here all the way up to here. Oh, no, it's centered around, how's that the upper edge of it? So it's plus or minus 0.0003. So interesting range of numbers on that one. And inside of jump right here, we calculated, oh, and there's, yeah, look at that. Because that's it's got the plus or minus of 0.0003 on it. So that's the exact calculation using R right here. Please tell me if you get it wrong. I'm going to throw 5 points on this quiz because of that. I just don't think that's fair. A lot of times when I think something's too hard or not fair, I'll throw extra points. But once again, if you get it wrong and you put it in, it's just an extra decimal. Email me, get your points right back. Or just message me. You can just be like, hey, Brian, I missed that. And I'll be like, hey, here's your points back. But for those who don't message me, I'm going to throw 5 points on for everybody. So you get a bonus if you're watching this and you email me. Let's take, I think Layla had one. And then Sam will do that next right here. Let's do that. I'm pretty sure. Here, let's see right here. I'm pretty sure I did it right, but can we go over the scores on a standardized test where the confidence interval increases from 98 to 90? Which ones? Oh, no, we got CADs. We got CADs. Thank you so much, Layla. You are correct. I was realizing that right in this moment. Which of the following is true or false? Using an alpha level, and is that chapter 16 CAD? Thank you so much. No, you're totally right. CAD and 320 is a lot of regression, and it's tons of fun, Sam, because we do coding and everything. And if you have questions about it, I might be able to talk about some today. I'm gonna try to find which one's CAD's questions on. But I really like 320. Like, it's just fun watching people learn how to code. So many people by the end of the class. Oh, found it. It's chapter 16. So many people by the end of the class. Thank you so much, Kat, for waiting. And everyone here is so awesome. 50 points, everybody. I was like, I won't forget Kat's question. And then I was like, forgot it. I'm sorry. Let's head over here. Let's do this. Thank you so much, Kat. Let's do this. Okay. Using an alpha level of 0.05, a p-value of 0.04 results in us rejecting null. True or false? We got this, everyone. Let's do this. Using an alpha level of 0.05, a p-value of 0.04 results in us rejecting null. When the p-value is low, reject the null. When the p-value is high, just let it fly. This is the alpha, which is the cutoff point of which you reject. It can be anything you want. You can just be like, I'm going to use an alpha of 0.08. Sure, whatever. You can pick the alpha. So if we get a p-value of this, would this result in rejecting the null? Oh, you're in the wave of students registering? Yeah, well, even if you're not in my class, Sam, you can always, and there might be a spot, if you're free summer session 1, a spot might open up in summer session 1. But even if you're not in my class, you can attend office hours and ask questions. So you can always ask questions. You can always swing by office hours. And this is very, very true. That's literally what we do. When the p-value is low, reject the null. So if you're not in my class, you can always swing by office hours. You can always ask questions. I'm always here to help. So just swing by, be like, hey, Brian, I'm wondering about this. How do I code this? What do I do here? And we work together on a team on 320. So you'll still get lots of help. And everyone else is great. I'm really excited to who I'm be working with next semester. My p-value was 0.069 for the last question. Should I put, what should I put since it's 4 decimals? Tell me your degrees of freedom, Layla, just so we can solve it right here. Tell me your degrees of freedom and tell me your test statistic, and I'll tell you what you should put. So put your degrees of freedom in the chat and put your test statistic, and I'll tell you the exact answer. And if it tells me you're wrong, if it tells us you're wrong, we'll just fix it. The alpha depends on the sample size, true or false? The alpha, and just think for a moment, you just get to pick alpha. Alpha's whatever you want it to be. Alpha's 0.02. Alpha's 0.08. Am I mentioning sample size at all right here? My alpha is completely what of my sample size? Awesome. I'll go solve this here in a second, Layla, right after this question. The alpha is completely independent. So is it C or B? So it's not always 0.05. It's not always 0.05. It's completely independent. We can pick it whatever we want. No. The same is false because the alpha level is set independently and does not depend on the sample size. It's completely independent right there. Good stuff. Good review. Let's put a little Eid music. So the next question is, when alpha is 0.01 and a p-value is this results in us rejecting the null. The p-value is high. Just let it fly. So that's definitely false. Only a p-value less than alpha results in rejecting the null. So be careful. They've got nonsense right here. Like, the statement is false because a p-value greater than alpha results in rejecting the alternative. We only reject the null or do not reject the null. I think I might have mentioned this today. Where did I put it on the notes today as we were talking through it. That you only reject the null or fail to reject the null. You only make two statements. Here we go. The only statements you make are you reject the null or you fail to reject the null. Those are the only two things you say. You have evidence for the alternative or you do not have evidence for the alternative. And that's related to reject the null, evidence for the alternative, fail to reject the null, do not have evidence for the alternative. So we don't say things like I reject the alternative or don't say that bad except word right there. Bad things. So the statement is false because only a p-value less than alpha results in rejecting the null hypothesis. Very true. Using an alpha of 0.05 and a p-value of 0.06 means the null hypothesis is true. Have we ever said the null is true? No, we don't believe the null is true. It would just be we don't reject the null. So this statement is false because a p-value greater than alpha only indicates there's not enough evidence to reject the null hypothesis. And we don't say accept the alternative. We don't say accept the alternative. We reject the null. If you say accept, it's a bad word. And a p-value greater than alpha indicates that the alternative is true. No. Awesome stuff right there. Great question. Let me look at Layla's right here. Layla said 47 degrees of freedom and a test statistic of this right here. So we're going to go over here to this question. And we're just going to go ahead and solve this. It was a two-sample test. 47 degrees of freedom. Test statistic of following. And there you go right there. The extra decimal is going to be a 7, Layla. And what I really like about this is you can always go right here to this and just ask it to round for you. This is what's so nice about coding. There you go. Don't have to worry about rounding stuff on your own and making an error. You can just say, hey, code, go round that for me. So the code will round it for you if you just put it inside this round function. So all it's doing, if you're looking at this right here, is it's just taking, good. We could just go here and call this x and just assign it like x is equal to that. Like it's just like a, and then we just would solve that right there. So you can do it in steps, Sam. So if you're looking at what we're doing right here, and Sam, if you want to download R in RStudio and start taking a look at this, you can always start out coding by just doing things like 2 + 2. That's code. Then you could go to something more advanced and say, let me think right here. What if I want to ask people a question here? We'll cut a segment right now. And I think there was another question. I think, Layla, if you want another question, let us know, because I think Layla might have had. You're welcome, Layla. So that one should be right there. We'll talk a little bit about 320 right here, and I can show you a little bit of 320. So in 320, we start out teaching you how to code. So if anyone's thinking about 320, like, hey, I want to check out more of this stats stuff. I want to see what you're doing in analytics. So what we start out with in 320 is we literally start with this. You're like, Brian, I'm too afraid. You do coding in class sometimes. And I'm like, what are you doing? We literally start by teaching you how to do 2 + 2. Then we teach you things like 2 divided by 2. Then we teach you things like 2 times 2. 2 minus 2, why not? All of this right here is code. But now let's get a little bit more advanced. Let's say you were to ask people, I want to do the one that's based on, yeah, let's do that next, or we'll do that here in about 3 minutes. You got it. And so now let's say we were to ask people their ages. And we go here and we say, let's talk to people and say, the first person we talk to is 19, then 22, then 24, then 20, and then 18. Does that make sense? I just have a bunch of numbers right there. They're all in order. This stands for concatenate things, or what is it? Also, there's another word it stands for join. It's basically joining them together in a vector. And what we have right here if you think about this with these numbers, is the exact same thing you would see inside of jump if inside of jump you saw this. Using something we know, that's what this looks like inside of jump. So all you have right here is a vector of numbers that you're creating. This is just a vector of numbers right here. That's all it is. And then in jump, we could go here to analyze distribution, and we could double click the variable, and we can go right here and get the distribution of the variables. And we can see things like a summary statistics, all this good stuff right here, just using that vector of numbers you see over there on the screen, which is right there on jump. It's just a vector of numbers. It's just been joined into a vector. That's all it's doing. There's the histogram. There's the summary statistics. Well, we can do the same thing in R. We can go right here and just type hist of ages. And here's the histogram. Where's my plots? Oh, figure too large. Yeah. There's the histogram right here. It looks a little bit different. I'm going to decrease font size so it'll look a little bit better. And there's the histogram. You can always increase, and it augments to the window, especially when you make the window bigger. And you can get a histogram right here. You can change the colors. A lot of fun stuff right there. You can also go right here and get a summary of it. You can get the mean of it. You can get the median of it. And we see we're just using this object right here. You can get the IQR of it. And you can just do all of these things just like this. You can get the min. You can get the max. And these are all just little functions right here that we can run. So we're just seeing tons and tons, standard deviation, just all of these things instantaneously. Like people are like, how do I solve the standard deviation by hand? It's like no one solves the standard deviation by hand. I mean, I'm sure someone does, but why? Why solve the standard deviation by hand? Or you could get the variance if you really wanted by squaring this, and there's the variance. So you can solve all these pretty instantaneously right here just by running all of these functions. You can get a box plot of it. These are all just little functions right here, and we can make them look nicer. But does this make sense here, Sam? Like, this is going to be the basics we're going to teach you. And you just saw how we created a vector right here. And then we just did a bunch of little tiny functions that have very simple names to it. And then this is what they're going to manipulate. Like, take the max of ages. Take the max, or take the standard deviation of the vector ages. We can even look at the vector right there by running that. So if you want to download R in our studio and take a look at it, let me know. I've got some tutorials walking through how to do these things. But yeah, so have you done any coding before, Sam? We're going to do Layla's question here. I'm going to hop to space. Have you done any coding before? Let's do the standardized. I think this is chapter 17, right, Layla? Let me see. We're on standardized testing. Have you done any coding before? If you've done coding, then it's like, you're like, yeah, that makes perfect sense. But if it's making sense now, that's even better. A lot of people haven't done coding, but a lot of people pick up on it really quickly. And they're like, hey, it makes sense. I see what's going on. But we teach everything from the bare basics. What you saw right there is about 40 minutes of lecture. Like, I'll go through it a lot slower in 320. But if you kind of saw it and it was just like jiving and you're like, I get what's going on right there, then you just got like 40 minutes of lecture condensed down into like a 3-4 minute speed run. I literally just opened it on the right question. I have not. This is my first class in stats major. Awesome. I'll be nearly done with psych in this fall, though. Awesome, Sam. I think you know I did psych also. Chapter 17 quiz. You got it. Let's do it. Here we go. Little Celeste music right here. Let's do this. The scores on a standardized test for 320 students in a non-traditional math class were compared to the 267 students in a traditional math class. Computer software was used to create a conference roll to look at the difference between the scores. And we get a difference right here of 6.385 to 12.215. Can anyone tell me theoretically what I need to do to get the margin of error? I'm just going to pause here for a moment. Got more than enough time to complete the whole question. Can anyone tell me theoretically what should we do to get the margin of error? Theoretically speaking, to get the margin of error, we should do what to the interval? Theoretically speaking, we should do what to get the margin of error? Always remember the margin of error is this for the interval. I think if you do a bunch of these, you'd be like, I would love that as a test question. But yep, I think you're right, Layla. Get the length of the interval, which is subtract the interval. So we're going to get the length of the interval by taking how far apart are these numbers. This is the length of the interval, the range of the interval, and then we're going to divide that by 2, and that is the margin of error, and it says do not round it. So we're just getting the length of the interval, which is upper minus lower, divided by 2, half the length of the interval. And just think about this. If the interval went from 6 to 12, you're welcome, Sam. Excellent work. Keep up the great work. Great job. If you have more questions, let me know. So if the interval went from 6 to 12, what would be the margin of error, Layla? If the interval went from 6 to 12, just only think about 6 to 12. Don't even use the decimals. If the interval went from 6 to 12, what would be the margin of error of the interval? Like, don't use the decimals. Just, like, use that to check your answer to be like, if the interval was 6 to 12, the margin of error would be this. It'd be 3. So that's a good indication right here. As long as we carried our decimals, we're probably on the right track. Always think about it like a simpler version to make sure you understand the concepts. Great job right there. If 90% confidence interval was created, would the margin of error be larger or smaller? So we're at 95. To do 90, I need to go inward. It's going to be less confident. So the margin of error would be smaller because the critical value is going to decrease. And as the critical value decreases, the margin of error decreases as the critical value decreases. That's just a lot of repeat. If the confidence interval was increasing from 98 to 99, the margin of error would be larger and all their blanks would increase. Exactly. Great job. Explain what it means to be the calculated interval means. We are 95% confident. And this interval right here is positive. My interval is completely positive, meaning that the non-traditional method was higher. So since the interval is completely positive, the mean for non-traditional was higher. So this is not student, not a student, but students, which is the mean. So you don't want to say a student because that's for individuals. This is for the mean. Students in non-traditional math classes score on average between this many points to this many points. Is it higher? Higher. This looks to be correct. So exactly. Not a singular student. We're talking about the mean. So it's all students, like the mean for students. And then since it's positive, the non-traditional, students in non-traditional score higher than the traditional scores. Does the interval result in suggesting that students who learn mathematics with non-traditional scores will have? Yes. I mean, gosh, they're saying will. It's good evidence. It's good evidence. They should say, is there good evidence that there is a difference between the two? That'd be a little better statistical wording. Yes. Because 0 is not contained, the entire interval is above 0, there is strong evidence to conclude that there is a difference. So does that make sense here, Layla? Our interval is completely above 0, so we think that if this was like an experiment, so they maybe should have said, does it say an experiment? It's the best way to show cause and effect. Like it was randomized, and then we had an element of control. So this right here would be good evidence. As long as we're not saying people get to pick which math class, because maybe people picked a certain math class who were better. But yeah, excellent work right there. Let's do a few maybe... Hop back here. I like this one. Got it. Oh yeah, Cad, if you want to send those, send me your interpretations and tell me which things to look at. So Cad, send me your interpretations. I see I've got 9 messages on Discord right now. Send me your interpretations. Tell me which ones to look at. I'll take a look, and I should be able to help out there. So with this right here, we're going to have students who are taking a math class, and they're going to have a score in June, and they're going to have a score in August. So you've got student scores. No, you've got a student score the first time they take the test and the second time they take the test. And so there's a problem with this for this chapter. This is chapter 17 right here. And you've kind of got the before and after. Now you'd hope students would do better the second time. So with this right here, the problem is that they're not independent of each other. So that does not meet the independent means assumption, which is that the mean for group 2 is independent of the mean for group 1, as in knowing someone's score in August would tell you nothing about their score in June, but there's probably some dependency right here. Like people's score in August depends on how they did in June. Because think, if you did well in June, you'll probably do better on a test in August because your knowledge would be dependent on how you did the first time. Hey, Scott, everyone. Yeah, Cad, send me your stuff right there. Send me like, hey, Brian, does this interpretation look well? Or how do I interpret this? Let me know. I think that's got it. We'll see right here. Are there any last few questions? We're about out of time, but let me know what questions you have. Last question. Yeah, let's do it. Researchers collected water from a mountain. Got the hiccups all of a sudden. You got it. Let's do it. Researchers collected water from a mountain. Where is it? Ah, we got it. Let's do it. Yeah, no. It's good. It's good to check, and then you get to kind of hear and walk through it. You know what's interesting about this one? We actually have 3 groups, but they're not going to compare all 3 groups. There's a way of doing that. It's an ANOVA. We're not doing that right now, but they're going to only compare the low, or what is it? It's like group L to group S. Looks like large, medium, small, right? Substrate type. They're only going to compare substrate type S to substrate type L. Now, this part right here is really easy. Now, I'm not saying like, oh, it's real easy, but what do you notice here that makes the answer to this super easy to where you're like, I've done that a lot. I know which one this is. Instantaneous, we're going to get the right answer here because we know the null has the what. Like, we got the right answer right here. Super quick. We get this problem. If this was on the test, we'd be like, free points because the null has the what. The null always has this. Something we always do, like, null has the this. We got it. The null has the what, which means it'll be this answer. So when we see this, we're like, yes, 3 points. We got it. The null has the equal sign. Great job, Kat, right there. The null has the equal sign. So if you see that on the test, you can eliminate anything where the null does not have the equal sign. Tomorrow, the rules, we're not going to change what the rules are. Independence assumption, independent groups is the 4th condition. They're calling this the randomization and the nearly normal. They're really nice to say that. I don't know. They should investigate this more closely. I just don't like how this one is having you check conditions right here. They don't really give you good enough information to check the conditions. Which conclusion would you draw? Here's our p-value. Here is our p-value. So what are you going to do? The p-value is super high. You're going to let the null what? The p-value is super high. Just let that null super this. What are you going to do? Since the p-value, which is here, which is the probability of our results or results more extreme happen by random chance variation given the null is true, on a t with 48 degrees of freedom, the t statistic was found to be 1.15. You're going to let that null fly. You're not going to fail to reject it. Just let that null fly. Just let it be. That's what let it fly means. There is not evidence. And remember, and this is a good review right here. Great question, Layla. We only do 2 things with the null. We either reject, and that means we have evidence for the alternative, or in this case, which means we just let it fly, we're going to fail to reject it, which means we do not have evidence. And if you see the way they're wording it, they're saying there is not strong evidence because we fail to reject the null. There is not strong evidence. Great stuff right there. Great question, Layla. Good one. It's good to double check these things and be like, okay, it gives me the p-value here. That means I do not have evidence for the alternative. I fail to reject the null because the p-value is so high. There's not evidence of a difference. Yes, I hope you got that 100 right there, Layla. Excellent work right there. We'll end off here with just some nice, happy music. Here we go. We'll go to this one right here. I feel like this one to end. Let's do this. Great work. If you have questions on the project, if you have questions on the assignments, let me know. 2 more days. We're going to do a Kahoot tomorrow. Should we do it during class again on Friday? That worked out pretty well. It's a good review. What do people think right now? Should we do the Kahoot tomorrow? I think we should do it on class on Friday, right? Because last time we were playing in class. It'll be the last class. We'll have some fun. We'll do a review after that. And tomorrow we'll be finishing up the chapters. So we'll put some of the Kahoot questions on the test. I'll be grading projects tonight. I'll be grading projects tomorrow. And then we'll be done. So I think we should do it Friday because people have this time reserved for class. That way it's going to be $100. $100 because people were donating you don't have to donate it. First person who won the Kahoot said, can I donate it to charity? And I was like, I can donate to my charity if you want. But then we decided it'd be good if we just put it to the final. And the next person said, hey, first person donate theirs to the final. I said, yeah. And they said, I'll donate mine to the final too. And I was like, okay, sure. Maybe they just want to win the big grand prize, the biggest Kahoot prize we've ever had of $100. We'll do $20 second and $10 third. So Friday, stay tuned for class. Play along in the Kahoot. Let's see who's going to win. We'll be back. I'll see everyone tomorrow morning. Bye for now, everyone. Bye. Bye, Puppet Shark.